So welcome to Math Stat 341 probability. And so actually it's been so long I forgot I have to hit the share button first. And so today is going to be a theoretical day. We have different types of days. Thursday is going to be an application day where we are going to see how can we actually use the stuff that we've been covering to do things that we might care about. So what I want to do today is I want to talk about one last example of differentiating identities. So we've already done some of these examples. We've done the Gaussian, we've done the exponential, we've done, I think, the geometric. I'm going to focus on the negative binomial. One of the reasons I want to focus on the negative binomial is it's probably the most confusing because it has a lot of different definitions. And so depending on who you're talking to, they will have a different definition of the negative binomial, just like we saw there were different definitions of the geometric. I want to then talk about sums of different types of random variables, sums of uniform, sums of Gaussian. These are extremely important for a lot of problems. And then as time permits, I want to talk a little bit about the Cauchy distribution. And this is a truncated version that someone gave me many years ago. The Cauchy distribution is one of the distributions you just need to know because you can argue as to whether or not it has a finite mean. It definitely has a 0 for the median. It has infinite variance. So when you're trying to test and see how robust a certain result, the Cauchy is a great thing to throw at it. It turns out that in some sense, the Cauchy and the Gaussian are related to each other. And they're related to a little bit of some of the things you might see in economics if you look at the stock market. And given that I know there's people in here who are also economics, I actually want to discuss some things that you might care about and might be able to use in other aspects of your education or life post-brilliance. So general items for today, the big one is integrating without integrating. So in Calc 2, the big lie is you leave thinking that you know how to integrate. You don't. You are trained so that if your professor is very kind and gives you nice integrals, you can evaluate those in closed form. Almost every integral cannot be done in closed form. And so I want to show you how we can do certain integrals without going through the pain of integrating. If you want more, here are just some of the links from previous years I've taught this, which goes through again and does the differentiating identities, does all those examples and whatnot. Okay, so we've started off last time, we did the Gaussian, we did exponential, we did geometric. And already in the geometric, we saw that there were two different ways you can look at things. Are we looking at the probability of a success or the probability of a failure? Are we waiting to count how long does it take before we get our first success or how long we're waiting until we get our first failure? It's not really a big deal, right? I don't really care if I'm waiting till I get my first success or my first failure. It's the same problem. The slightly different problem is how many successes do I have before I have my first failure, or how many failures do I have before I have my first success? That's a little bit different than the previous question. What does it differ by? How much does it differ by? So if I'm waiting for my first success, or I'm counting the number of failures before my first success, how do those numbers differ? They differ by 1. It's not a big deal. Right. Anybody see Indiana Jones in the original? All right, so it's like the extra 1 you got to remember to subtract off. All right, in something like that, it could matter. This is really easy to translate back and forth if I'm off by 1 in my counting. Am I counting the total number of attempts, or am I counting the number of failures before the first success? Well, they just differ by 1. What it means is you have to be careful about which formula you use. This is the negative binomial. It should look a lot like the geometric with r equals 1, except I have things to the kth power rather than k minus 1. Over here, this is the geometric k. Whoa, that's a thick k. Here, k is in 1, 2, 3, ... We're counting failures. Oh, no, sorry, counting attempts. And so what is the minimum number of attempts you need before you succeed?
1.
1. I don't care how good you are. Okay? You should not succeed before you attempt. I was at a conference years ago where they were giving prizes to students, And some students, again, these are math students, they're smart people. They realize something is suspicious if you give the prizes before everybody speaks. You would think a math conference would be smart enough not to do this. It's really obvious when you have the award ceremony before everybody talks. So you have to have at least one attempt before you have a success. So here, we're not going to allow k to be 0. In the definition over here, however, I can definitely have k be 0. I'm counting here the number of failures. And that's why here, k is in 0, 1, 2, ... So there's slight differences between them. So if you go to Wikipedia, source of all knowledge, fountain of all wisdom, they even have a really nice section where they talk about different texts and even different parts of this article. It's great. Not even consistent throughout the article. So you've got to be really careful when you're reading things that you're using the correct notation. This is similar to the issue sometimes mathematicians and physicists have where they have slightly different normalization conventions. All right, so let's talk about how we want to do things. I have decided not to prepare the lecture and to let you choose how you want to count things. All right, do you want to count the number of attempts? Do you want to count the number of failures before we have? The formula that I wrote over here is counting the number of failures. So this is counting how many failures do we have before we have how many successes do you think? Not one. Look at this. What would you guess the number of successes? I'll try to zoom in. So how many successes do you think we have? R. So if we have k failures and r successes, it's k plus r attempts. You could, of course, recount, and it all comes down to what do you think is going to make the algebra nicest? Probably this is the one I want to do, is this is the one I listed. And I can always add, if I know the number of failures, I can add r to it afterwards. And it's just, trying to keep my exponents nice. Does this seem like a reasonable version to use? All right, so let's see that this is reasonable. What does it mean to have r successes in k plus r attempts? So let's think we have a bunch of boxes. Box 1, box 2, box k plus r minus 1, box k plus r. If we want to have exactly r successes in the first k plus r attempts, what must the last attempt be? What must the last attempt be? What must be the result? It has to be a success. Otherwise, I would have obtained my r successes earlier, or I won't have r successes. So what must be true in the first k plus r minus 1? How many successes do we have? We have r minus 1 successes. And how many failures? Okay. So how many ways can I arrange s successes, r minus 1 successes and k failures in k plus r minus 1? How many ways are there to arrange that? I've got k plus r minus 1 boxes. I have to choose r minus 1 of the boxes to be a success. How many ways can I do that? K plus r minus 1, choose r minus 1. This is the number of strings. Now, each string has the same probability. I don't have a different probability of a success later or earlier. In a lot of things in life, that's not true. You might get tired, right? What's the probability? Well, I have k failures, that's 1 minus p. And then I have r minus 1 successes in the first group, and then one success at the end. So I have R successes total. And that's where the formula comes from. So this is our formula for the probability of having exactly K failures and R successes. Now, I know it's been a while since you've seen me. What is the first thing you should do after you know that something's a distribution? What questions do you ask it? Yes. Well, so we should definitely do that. So I'm going to assume that we have done that we know it's a probability distribution, it sums to 1, and it is non-negative. So now what's the personal questions you want to ask? Yeah, what's your mean, what's your variance? Once you get to know it, you can ask about kurtosis and skewness, but what's your mean, what's your variance? Now, to do that, we're going to have to take this and either multiply by K or K plus R, depending on do we want to count the number of successes or do we want to count the number of attempts. Now, we need to prove that this sums to 1. How do you prove this sums to 1? To some extent, we've basically done this by our story. This is the probability that you have exactly R successes in the first K plus R. And K could be 0, could be 1, could be 2. This is like the geometric problem we saw in the first day of class, the basketball game. Because we have a story, we know that this does sum to 1. You could try to prove directly that this sums to 1, which is a challenge. This is the advantage of proof by story. I know I have a bunch of disjoint things. There must be some number of failures before I get my R successes. And I can't have exactly 3 and exactly 8 failures before I get my first R successes. So I have a bunch of independent events, I sum them all, and that's going to be the probability. Something has to happen. So I do know that it sums to 1. I do know it's non-negative. Now we want to calculate the mean. Okay, so we're going to do this 3 different ways. We're going to do it by differentiating identities, we're going to do it by linearity of expectations, and we're going to do it by a recurrence relation. Okay? Now, if you're going to differentiate identities, you need an identity. So we know the probability, exactly K failures is equal to K plus R minus 1, choose R minus 1, 1 minus P to the K, P to the R. We need an identity if we want to use differentiating identities, right? Does anybody know any identity involving these probability coefficients? Okay, but that's for like X plus Y. And unfortunately here we've got something changing with K. It actually goes back to a comment you made earlier. Yeah, it sums to 1. That's the only identity we know. We know the sum, K goes from 0 to infinity, of K plus R minus 1, choose R minus 1, 1 minus P to the K, P to the R equals 1. We can now differentiate. What variable should we differentiate with respect to? There's only one variable that we have to differentiate. I'm sorry? K. Not K. K is an index of summation. We sum over K. K is a dummy variable. We can't differentiate with respect to K. R is the number of successes. What's the only thing that's left? P. We have to differentiate with respect to P. What rule will you have to use to differentiate with respect to P? Product rule. No one wants to use the product rule. So what we're going to do is, this is the same as the sum, K goes from 0 to infinity, K plus R minus 1, choose R minus 1, 1 minus P to the K equals P to the negative R. Let me move it over to the other side. I'll differentiate and then I'll bring it back. And this way I'll avoid having to use the product rule. It just makes my life easier. So much of math is about making your life easier, finding a good way for the algebra. This is why I'm really spending time today highlighting this in excruciating detail. Okay. Now, I'm assuming that everybody spent their spring break learning analysis as a surprise to me, that you've now mastered not only undergraduate, but graduate analysis. And there's no need for me to talk at all about how to justify interchanging an infinite sum and a derivative, because you're all experts at that. Excellent. So as you learned over your spring break, or if you haven't, if you take an advanced math class, we now differentiate with respect to P. So we have to worry about what level things are going to be at. So I'm going to initially take the derivative with respect to P. I won't worry about justifying interchanging the sum and the derivative. So I'm going to get the sum, k goes from 0 to infinity, of k plus r minus 1, choose r minus 1. A k is going to come down, which is great. And I'm going to get a 1 minus p to the k minus 1 equals minus r p to the minus r minus 1. This is kind of looking good. But I no longer have a 1 minus p to the k. I've got a 1 minus p to the k minus 1. What could I do? Yeah, multiply by 1 minus p. Then this is going to not change its power. So let's not take the derivative with respect to p, but multiply by 1 minus p and then take the derivative. And so now when we do that, the only change is now we have a 1 minus p over here. Now notice that this is almost the mean. It's almost k times the probability. It's missing a factor of p to the r. Let's multiply both sides by p to the r. And so we then get the sum, k goes from 0 to infinity, of k times k plus r minus 1, choose r minus 1, 1 minus p to the k, p to the r. Oh, whoops, I made one mistake. When I differentiate 1 minus p to the k, I don't get k. What do I get? I get negative k. Right? I knew there had to be a mistake because on the next line I was about to get the mean as a negative number. My daughter realized that Power School was calculating her grade incorrectly because she hasn't lost any points all semester in one of her classes, and her average wasn't 100. So she knows there has to be some mistake somewhere. Your average can't be lower than your lowest score. Over here, if I'm taking the mean of a distribution that only takes on non-negative values, I should not get a mean that's negative. So I knew that there had to be a minus sign mistake. So I'm going to get r. I multiply by p to the r, so that's going to give me a p to the minus 1. So I'm going to get a 1 minus p over p. And so we get the mean number of failures before r successes is r times 1 minus p over p. Is there any way that you might want to rewrite r times 1 minus p over p? How could we rewrite this in a more illuminating manner? So how could you rewrite that?
1 over p minus 1. And if we're assuming p isn't 0.
So we will assume p is not 0. If p is 0, what's the probability of your success? 0. How long is it going to take? It's going to take you a long time to get our successes when you have no chance for success. So implicit in all of this is the assumption that p is not 0. So you should always be asking, is this formula reasonable? And it makes sense because if p was 0, it would basically say you would have to wait infinitely long to get our successes. But how could you view r times 1 minus p over p? How might you expand that?
So do r over p minus r.
Good. Now, this is the mean number of failures. Instead of failures, what could I look at? the mean number of so what did we say was related to, instead of looking at the number of failures, we could look at the total number of attempts. How do they differ? They differ by R. So it's just R over P. Okay, so in terms of when I see 1 minus P over P, I view that as it's R over P minus R. Okay, that minus R is really nice because the difference between failures and attempts is this extra factor of R. Okay, now, what is the easiest value of R to understand? Zero, but then we're not allowed to talk about zero. Although they would say that there's no attempts needed before you don't succeed. So what would be the next value of R to understand? One. We've seen this before. When we looked at a geometric random variable, how long do we have to wait for the first success? If the probability was P, it was 1 over P. So if P is 1, the success is immediate. If P is 0, you have to wait infinitely long. What this is saying is there is an interpretation to what we have here. Because it's R over P, you can view this as, hey, wait a minute. This is almost like I wait for my first success, and after succeeding my first time, I wait for my second success, and then I wait for my third success. So this suggests view as a sum of R independent geometric random variables with probability P. That makes a lot of sense. If I want to wait until I have R successes, wait until you have the first, then wait until you have the second, then wait until you have the third. This is very similar to the crackerjack problem. So this is giving us the second way of looking at the problem, linearity of expectation. So if, let's say, X, RP is the random variable to have R successes with probability P of success, and it's counting attempts, then it is the sum of R independent geometric P, random variables waiting for first success. So, XRP let's say it's geometric 1P plus geometric 2P plus geometric RP. We just have R independent copies. And so by linearity of expectation, what's the expected value of XRP? It's just going to be R times the expected value of any of the G's, which we knew from before is 1 over P. This is also another way to prove our formula for the probability of having K failures before R successes, is we now have a sum of independent geometric random variables, and if only later today we would talk about how to find formulas for sums of independent random variables, we could then apply that and show that this is the correct formula. So it all ties together. All right. But, 2 proofs is not enough. Let's do a third proof. Let's do a recurrence relation proof. All right. And I may get this slightly wrong, and I apologize as to, do I want to do attempts or number of failures? Let's do attempts. Let's try doing attempts. Let's let mu RP equal the average number of attempts before our successes with, probability P of success each time. Okay. So we claim, or we conjecture, that mu RP is just R over P. And we know mu 1P equals 1 over P. That's the geometric case, which we've done. So we know the first case. Anybody know what proof technique might be useful now? Induction, right? We know the first case. We now want to prove the general case. So again, you are going to forget most of the material you learn in most of your classes. Okay? This is the 21st century. It's not a big deal. The internet exists. If the internet does not exist, you have bigger problems than what you've forgotten. Okay? What I want you to leave this class with is knowing how to attack different things. What mindset can I adopt? What's a good way of looking at things? That's going to be the skill that will serve you. Does this look like induction? And if it looks like induction, then I just go into my induction mode and let me try to do this by induction. So let's prove it by induction. So proof by induction. So one is base case is done. So let's assume mu RP equals R over P. Then let's calculate what mu R plus 1P is. So what could happen on the very first toss? So what are the possibilities for the first toss? Success or failure. If it's a failure on the first toss, then it's like we've just started the game all over again. If it's a success, then we need one fewer success. So let's assume we got a success. Then how many more successes do we need? We need R successes. So it would be mu RP plus 1 if we got a success. Right? So I want to calculate how many attempts does it take on average. If my first attempt was a success, I have to add 1. And now I've just reduced, instead of waiting for R plus 1 successes, I'm just waiting for R successes. Or my first success was a failure. And if it's a failure, how many successes do I have to wait for? R plus 1. So then that would be mu R plus 1 P plus 1 because I just had the attempt. And so notice the quantity we're trying to solve is on both sides of the equation, and the coefficient in front of it is not 1. So because it's not 1, we can actually solve for it. And so let me just write this on the next page. So we know by assumption, this is R over P. So we get mu R plus 1 P equals R over P plus 1 times P, okay, plus 1 minus P mu R plus 1 P plus 1 minus p. So let's bring the 1 minus p mu r plus 1p to the other side. Well, the coefficient there is 1. 1 minus p is just going to be p. So we get p times mu r plus 1p is r over p plus 1 times p. So that's going to be r plus p plus 1 minus p. And that should just reduce to r plus 1. And so we get mu r plus 1p is r plus 1 over p as desired. And so we've now solved it 3 different ways. We solved it by differentiating identities, we solved it by linearity of expectation, and we solved it by a recurrence. So there's lots of different ways of looking at these problems. You have to find which way is the best way for you to go through the algebra. This is very similar to the bacteria problem that we saw. And again, it's incredible how many things can be solved by good recurrence relations like this. This bring it over method where you get the unknown on both sides is powerful so long as the coefficient isn't 1. If the coefficient was 1 on both sides, then when you bring it over, it just removes itself and you can't solve for it. Okay. That should be more than enough ways of doing the negative binomial. This is just a great way to review the techniques. We calculated the mean. You should now calculate the variance. What's nice is if you're calculating the variance, it doesn't really matter if we're doing attempts or failures because they differ by shifting everything. And that's not going to change the variance. So you can now just calculate the second moment. Okay. And so now it's time to do sums of random variables. So let's just recall convolutions. So if x and y are independent random variables with densities f of x and f of y, if z equals x plus y, then we showed that the density of z is the integral of the density of x at t times the density of y at z minus t dt. This is a wonderful formula. If you think about it, well, if I want x plus y to be equal to z, if x equals 5, then y has to be z minus 5. If x equals 8, then y has to be z minus 8. So in general, if x equals t, then y could be z minus t. I could use the letter x rather than the letter t, but that's putting like extra special emphasis on x, and so I'm just using the variable t. Do you think it matters the order in which we add x and y? No. So we often write, fz of z is fx star or convolved with fy evaluated at z. And again, it turns out that it's the same as fy star fx. And you can prove this directly by doing a change of variable. So it all comes down to now, can we do these integrals? I showed you earlier, and this is the nice thing about saving the slides, is I checked what happens if you add 2 uniform, 4 uniform, 8 uniform, and you can just see that while we can write down a closed form expression, it becomes a nightmare. And so one of the big themes of the second part of the semester is going to be approximating these sums when you have many summates. So rather than trying to get a closed form expression, let's just try to get something that's close. Okay. So now let's put in different choices and go through the calculations. So I'm going to share some slides for what happens if we choose one of the simplest things possible. What do you think would be the nicest function to integrate? Nicest probability distribution you can think of. Uniform, right? The uniform is going to be the easiest because the integrand is going to just be 1. This is one of the few integrals we can do. The difficulty with the uniform is figuring out what are the bounds of integration. Okay? So let's go through and start looking at. So let's have sums of independent, identically distributed random variables. Let's say x1 and x2 are uniform. And let's make them uniform in 0, 1. Right? So that means the probability distribution is just 1. If they were uniform on 0, 5, the density would be 1/5. And I want to calculate what is the density of x1 plus x2. If you've ever played games with die, if you have to roll 2 die like backgammon or Monopoly, 7 is the most common sum, and then 2 and 12 are the least likely. It's a nice triangular function. And we're going to see that here in a moment. So I need to calculate the integral from minus infinity to infinity of the density of the first, which I'll call P, and the density of the second. Now, this is where almost all mistakes are made. The integration is trivial. It's making sure you have the right bounds of integration. So the first one, my density is not 1 everywhere. My density is only 1 for inputs between 0 and 1. So over here, because I have a P of t, this is 1 so long as t lives between 0 and 1. If I take t equals 5 or t equals -2, it's going to be 0. So I can replace this with a 1 as long as I restrict myself to t between 0 and 1. And that's how I get from the first equal sign to, the second equal sign to the third. Instead of integrating from minus infinity to infinity, I'm now integrating from 0 to 1. And now I have the second one. Okay, well, what about the second one? I need the input to be between 0 and 1. So I want 0 to be between x minus t and 1. So again, this is really straightforward integration. It's just making sure you don't make a mistake on the bounds of integration. Well, if 0 is between x minus t and 1, t is my variable. That's the same as t goes between x and 1 plus t. And this is where things can start to be unpleasant. If x is large, let's say x is 1.5. What's the smallest t could be if x is 1.5? So if x is 1.5, and I want x minus t between 0 and 1, what's the smallest t could be?
0.5.
0.5. What's the largest t could be?
1.5.
1.5, which is not entirely in the interval 0, 1. So unfortunately, the restriction of t between x minus t between 0 and 1, not all values of t are going to necessarily work depending on what x is. And so I'm going to have to figure out what the bounds of integration are, and it's not surprising that it's going to depend on x. If it didn't depend on x, then I would get that the probability of the sum is uniform, and I would get uniform plus uniform is uniform. So I have to figure out, how do the bounds depend? And so before doing that, I want to emphasize a key mathematical idea. Reduce to simpler cases whenever possible. So do we agree that if x1 and x2 are uniform 0, 1, the smallest the sum can be is 0, the largest the sum can be is 2? I claim that the sum is symmetric. And symmetric about what value? What do you think the symmetric value is for this? So the sum is between 0 and 2. What do you think it would be symmetric about?
1.
About 1. And so here's the quick proof. If xk is uniform 0, 1, so is yk, which is 1 minus xk. And so instead of looking at x1 plus x2, I could look at y1 plus y2, which is going to be 2 minus x1 plus x2. What's the largest y1 plus y2 can be? 0. I'm sorry, 2. The smallest it can be, 0. So really, the sum of x1 plus x2, that's going to have the same distribution as the sum of y1 plus y2. So I claim I really only need to understand what's going on for sums up to 1. That, if I look at, trying to figure out what's going on, here's 0, here's 2, here's 1. If I can figure out what's going on over here, I can basically copy and figure out what's going on here. That if x1 plus x2 equals 1/4, that's the same as y1 plus y2 is 7/4. So, the probability of a sum of 1/4 is the same as the probability of a sum of 2 minus 1/4 equals 7/4. If you don't see this, not a big deal. You just have more integration to do, more sums to do. You have to break things up into cases. But what I'm saying is, if I can understand what's going on between 0 and 1 for the sum, I can figure out what's going on from 1 to 2. Okay? All right. So let's start looking at. So we had the integral from 0 to 1 of 1 times p of x minus t. And, this is just a clear copy and paste from an earlier slide. We know x minus t has to be between 0 and 1. So x is greater than or equal to t, and it's less than or equal to 1 plus t. So you give me a value of x, and that's going to impact what t is. And so again, we have to be careful. If x is greater than 1, well, we know t can't be larger than 1. And so the bounds split depending on where x is. That's why I wanted to just do that previous argument, so I can just reduce to the case when x is at most 1. And so now let's do the case when x is at most 1. Well, if x is at most 1, I don't have to worry about x being less than or equal to 1 plus t. No matter what value of t you give me between 0 and 1, x is always going to be less than. So this is trivial if x is less than or equal to 1. Right? T is non-negative. So clearly 1 plus t is going to be greater than or equal to x because x is at most 1. So that part becomes trivial. And so now the only part that really matters is that t is less than or equal to x. So I now just integrate from 0 to x. And this is our lucky day. The function we're integrating is the function, technically it's 1 squared. It's really no different than integrating the function 1. Okay, I integrate the function 1 from 0 to x, I just get x. And so you get that the density is 0 at 0, goes all the way up to 1 at 1, and because of the symmetry we just argued, then it has to fall down to 2. And so here is a proof that the sum of two uniform random variables is a triangle. What should the area of the triangle be? What should we have for the area of the triangle? 1. It's a probability distribution. Okay, good. It's got a base of 2. It's got a height of 1. Good. The area under the triangle is 1. So everything looks consistent. This is great. Now we could try to figure out what's the sum of 3 uniforms or 4 uniforms. 4 uniforms I think is nice because you can group it as the sum of 2 uniforms plus the sum of 2 uniforms. So triangle plus triangle. And it gets worse and worse and worse. And the boundaries of integration get harder and harder and harder to explicitly write down. You saw the Mathematica code and display a while ago where it just got to be a nightmare. And so rather than calculating things exactly, you reach the point where you can say, I can approximate it really well. The key thing to note is a uniform plus a uniform a uniform? No. Usually in life, things don't stay the same. So now, let's look at Gaussians. So I'm going to just start off a little bit with some simple things. Let's assume x1 and x2 are normal random variables with mean 0, variance 1. And we'll assume they're independent. So the expected value of the sum is the sum of the expected values. That's just going to be 0. The variance of a sum is the sum of the variances. That's just going to be 2. And then the question is, what is the shape of a Gaussian plus a Gaussian? Uniform plus uniform became a triangle. So something is stable if the shape is the same when you add it to itself, when you add 2 independent copies. That doesn't mean it has the same mean. That doesn't mean it has the same standard deviation. It can't. If I add 2 copies, the standard deviation has gone up by a factor of √2. That's fine. It's still in the same family. It's still going to be hopefully a normal distribution. And so it turns out the normal is a stable distribution. Normal plus normal is normal. Anybody want to guess what another stable distribution is? It's been mentioned today as a distribution you should know.
Cauchy.
Cauchy, right? The Cauchy and the normal actually sit together in some kind of high-level family, which has tremendous applications in economics. In terms of, if you've ever heard of the random walk on Wall Street and trying to model the stock market, the normal random walk model does not have enough days of large deviations. The Cauchy model does. And so how many of you are doing economics as well? This is something you need to know, and I'll explicitly send you some stuff to look at if you're interested in stuff like this. So we want to show normal plus normal is normal. The good news is the bounds of integration are going to be much easier because we're just going to be integrating from -infinity to infinity. The bad news is the integrand is much worse. It's a trade-off. Okay, so let's assume we are able to show 2 normals with mean 0 sum to a normal. And again, if the means aren't 0, I can trivially adjust things because all the mean does is it shifts everything. So if I understand the distribution of 2 things, if I shift the mean of the first one by μ1 and the second by μ2, I just shift the sum by μ1 plus μ2. I can just, without loss of generality, I can make the algebra a little bit simpler by saying mean 0, add the means later if you want. It's going to be bad enough as is. Any savings I can do in the algebra, I want to do. So let's just assume all the means are 0. Imagine we can show Gaussian plus Gaussian is Gaussian. Then imagine we had n Gaussians. Well, by the inductive assumption, the first n-1 are Gaussian. The last one is Gaussian. Gaussian plus Gaussian is Gaussian. So all we have to do is show that the sum of any 2 Gaussians is a Gaussian, and then we know the sum of an arbitrary finite number of Gaussians is Gaussian. It's important, however, that we do it for arbitrary standard deviations or variances. I can't just assume that the variance is 1, because when I do this by induction, I'm going to have n-1 summands here. So I have to do things with general standard deviations or general variance, but I can't assume mean 0. And this is the argument we've seen many times by just grouping. So once you can do it for 2, you can do it for 3, you can do it for 4, you can do it for any finite number. Right? Now we just have to do this. All right. Let's look at the integral we need to do. So it would be the integral from -infinity to infinity of the density of the first one, let's say at t, the density of the second one at x minus t dt. So when you put everything in, it's going to be 1 over 2 pi sigma 1 sigma 2, because I've got the square roots coming twice. So the square root of 2 pi reinforces. Square root of sigma 1 squared is just going to be sigma 1. Then I will have the integral from -infinity to infinity, e to the negative t squared over 2 sigma 1 squared, e to the negative x minus t squared over 2 sigma 2 squared dt. That's the integral we need to do. Okay. So my goal, and we have till 11:10, right, is to do as little integration as possible. I want to introduce you to one of my favorite techniques in probability. Have you ever heard the expression, I'll know it when I hear it? I'll know it when I see it. If I give you something that I know is a probability distribution, and I know most of it, I can often figure out the rest. I just need to figure out what is the dependence on the variable. This is called the theory of normalization constants. If I have something that looks like some constant e to the minus x over 3, what kind of distribution is this? What kind of distribution do you think this would have to be? We've seen this before. It has a name. Exponential. Which exponential? What do you think the parameter is? 3. What does a have to be then? Yeah. So this is the theory of normalization constants. If we know it is a probability distribution, the x dependence is that of an exponential with parameter 3, so a equals 1/3. We don't have to compute a. Because we know it's a probability distribution, when the dust settles, a has to be 1/3. I could compute a if I wanted to, perhaps, but there's no need. This is similar to at the beginning of the day when we had the negative binomial. We knew that the sum had to be 1 because we told a story. Do I know that the sum of 2 independent random variables is a random variable? Yes. So its density must integrate to 1. So when I'm calculating this, I'm going to get a tremendous amount of crap. I don't care what the crap is. I just care about understanding the x dependence. If the x dependence is a Gaussian, then I know it must be a Gaussian. And I know what the normalization constant of the Gaussian has to be. I don't have to keep track of everything. And if it's going to be a Gaussian, since they both have mean 0, what would the mean have to be? So they both have mean 0. What's the only possible mean that the sum could have? 0. What's the only possible variance it could have if the variance is a sigma 1 squared and sigma 2 squared?
Sum.
The sum. So if can show the x dependence is that of a Gaussian, must be a normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. There's nothing else it can be. So all I have to do is show that when I finish the integration with respect to t, it looks something like e to the negative constant x squared. That's it. Once I get that, I'm done. Okay? So let's just focus on, we have the integral from minus infinity to infinity, 1 over, I'll keep it in 2 pi, sigma 1, sigma 2, e to the negative t squared over 2 sigma 1 squared, e to the negative x minus t squared over 2 sigma 2 squared dt. So the exponential is negative 1 over 2 sigma 1 squared t squared minus 1 over 2 sigma 2 squared x minus t squared. And I claim this equals minus at squared plus b t minus x squared. And actually, I'll make that a plus. I'll make that a minus b. So I claim, oh, sorry. I need to put in a c over here. Plus cx squared. So let's think about what's going on. So we have minus 1 over 2 sigma 1 squared t squared minus 1 over 2 sigma 2 squared x squared minus 2xt plus t squared versus minus at squared minus b t squared plus 2c tx plus c squared x squared. So this side, I'm going to have minus a plus b t squared minus 2bctx plus this is right. Minus b c squared x squared. So the question is, do you think we can match everything? So on this side, we've got a minus 1/2 sigma 1 squared minus 1/2 sigma 2 squared t squared, right? Then we have minus 2/2 sigma squared, the minus reinforced, I think, plus the 2's cancel, xt over sigma 2 squared, and then minus x squared over 2 sigma 2 squared. So we want to match things. And so I can write this term over here as bc times c x squared. So first, can I choose a value? I've got three things. I've got the t squared terms. I have the xt terms. And then I have the x squared term. I just have to show that I can find coefficients a, b, and c to match. I've got three things. I should be able to find a, b, and c to make them match. It would be wonderful if it was a t squared plus b xt plus c x squared. Then that would be really easy to match. If you look at it though, can I choose bc to match the xt term? Yeah, there's more than one choice of bc that works. Once I have that, can I make the x squared match? Yes, because I have that extra factor of c. So first, so we choose bc to match the xt terms. So this is really important. Does everybody agree I can choose bc to match the x term, the xt terms? Then we choose c to match the x squared terms, and that forces b on us, right? Because once we've chosen c, b is now forced. We now have to match the t squared terms. Well, fortunately, it's a plus b. So no matter what b is, I can just adjust a, and so now we can find a. Now find a to match the t squared terms. So this proves that we have such a decomposition. I could do the algebra, probably make a few mistakes, but I could do the algebra and explicitly tell you what a, b, and c are. It's not that hard. But there's no need. I just need to know that an a, b, and c exist. A, b, and c exist. If you want to roll up your sleeves and do the calculation, more power to you, go for it. But at a high level, I just need to know that I have such a decomposition. Okay, so now that I have that decomposition, I can continue. And so I'm going to have the integral from minus infinity to infinity, 1/2 pi sigma 1 sigma 2 e to the negative, and then I think we said it's going to be minus, oh shoot. I did this the wrong way. I apologize. I didn't want. I wanted this to be x squared. because there's an x squared over here. This was just a typo. Right, because I've got to get the x squared term over there. So now I match the x squared terms. Oops. And so that becomes an x squared, right? And so over here, okay, so this changes the algebra ever so slightly over here. So now, okay, so now we have, all right, so let me just, apologies for that. Best thing to do in a case like this is just stop, erase, and just redo. So I wish somebody had noticed the algebra mistake earlier. Okay, so now how am I going to get an x squared term? I'm going to have a negative a, or I could have a minus bc squared, right? How can I get a xt term? That's going to be a minus bc 2xt, and then I have a minus b t squared. Okay, so looking at this, okay, so which one is the easiest to match? It's going to be, I think, the t squared, right? So match t squared, that forces b on us. Now we match the xt, we know b, that forces c on us. And now, can we make the x work? Yes. We match the x squared, that forces a. So we still have the way to, the algebra is actually a little bit better once we do the correct algebra. Okay, so now that we have that, we know we have a way of writing it as minus ax squared minus b times all that. Okay. So I'll just put that over here as to, this is what, whoops. So this is what we had. So it's minus ax squared e to the minus b t plus cx squared dt. All right, I can pull out the 2 pi sigma 1 sigma 2. I can pull out the e to the minus ax squared because there's no t dependence. I now have the integral from minus infinity to infinity e to the minus b t plus cx squared dt. But as t goes from minus infinity to infinity, I can just shift t, right? Let u equal t plus cx. So this is just 1 over 2 pi sigma 1 sigma 2 squared e to the minus ax squared integral minus infinity to infinity e to the minus b u squared du. That's just a number. I can figure out what number it is in terms of b, but this is just some number. Let's call it capital B. So we get big B over 2 pi sigma 1 sigma 2. Oops, there's no square here. E to the minus ax squared. Notice that this looks like a Gaussian. The x dependence is that of a Gaussian. So it has to be a Gaussian. We know it's a probability distribution. It looks like a Gaussian, it has to be a Gaussian. Because it's a Gaussian, the normalization constant must be the normalization constant for the Gaussian. And we know that it has to be a Gaussian with variance sigma 1 squared plus sigma 2 squared. So A has to be 1 over 2 sigma 1 squared plus sigma 2 squared, and b over 2 pi sigma 1 sigma 2 has to be 1 over the square root of 2 pi sigma 1 squared plus sigma 2 squared. You can go through and do all the algebra and get that if you want. I'm trying to really show you the power of the theory of normalization constants. I know a lot of professors, I had some of them when I was young, who would actually assign problems like that just so you would appreciate the theory. If this is not connecting with you, I urge you to go through and do it by brute force and not make any algebra mistakes. When the dust settles, if you do everything correctly, you will get those values for A, you will get those values. But at a high level, there's no need, and this is going to be very useful later on for trying to understand what is the behavior for sums of different independent random variables. This is absolutely amazing that we just need to get close and we can correct. So as long as I can see that it's a Gaussian, I know that if it's a Gaussian, it has to be a Gaussian with mean zero invariance, sigma 1 squared plus sigma 2 squared. So boom, that's what A has to be. So this is, again, one of my favorite techniques. It's a little bit hard to use, but it's extremely useful. How many of you have seen the beta distribution in statistics? No one has seen the beta distribution in statistics. Okay, then we will definitely see the beta distribution later. These are challenging integrals to do involving generalizations of factorial functions. But again, we can play this game of identifying what things are. And you say, look, I don't have to evaluate it exactly. I just have to sniff out the x dependence. And as soon as I sniff out the x dependence, the normalization constant is going to come to me for free. Okay. So Gaussians are stable. Gaussian plus Gaussian is stable. Uniform is not stable. And so this leads to one of the most natural questions you can ask. What else is stable? And if you have two different things that are stable, are they somehow in a larger family? Is there some family that actually connects a Cauchy distribution to a Gaussian? And there is, and it does have applications in economics. So we have talked about the Cauchy distribution before. And so this is just a review slide. Its probability density is 1 over pi, 1 over 1 plus x squared. It's non-negative, it integrates to 1. And then we are going to use proof by language. What is the tangent of the arctangent of x? Or in English, what is the tangent of the angle whose tangent is x? X, right? So tangent arctangent of x is clearly going to be x. And so we can use this to get tangent prime of arctangent of x times arctangent prime of x equals 1. And so we can solve for arctangent prime. It's 1 over tangent prime at arctangent. We know the derivative of tangent is 1 over cosine squared, which is the same as secant squared. And then you can play some trig games, and we've done them before, to get the, the cosine squared of arctangent of x is 1 over 1 plus x squared. And this is just from drawing the triangle, where if I want an angle whose tangent is x, we'll make the vertical x and make the base 1. So the hypotenuse is the square root of 1 plus x squared. So the cosine of the arctangent is 1 over square root of 1 plus x squared. So the cosine squared is 1 over 1 plus x squared. So this is just a review. We've done the Cauchy distribution before. It clearly does not have a variance that's finite. If I multiply by x squared and integrate, I'm integrating x squared over 1 plus x squared. Well, when x is really large, x squared over 1 plus x squared is basically just 1. So the Cauchy distribution does not have finite variance. So whenever you're testing things to see how general is the result, the Cauchy should be one of your go-to examples. Uniform, exponential, Gaussian, these are all nice. Uniform has finite support. Gaussian, exponential, they all decay very rapidly. What happens if you don't decay very rapidly? It turns out the Cauchy distribution is stable. So Cauchy plus Cauchy is Cauchy. I will make that extra credit if anybody's able to do this. The simplest proof I know uses complex analysis. And it becomes trivial if you know complex analysis. Complex analysis converts integration to algebra. It converts integration to finding a certain term in a generalized Taylor series expansion. So if you continue on the pure side, if you take classes like complex analysis, not only can we handle distributions like 1 over 1 plus x squared, we could do 1 over 1 plus x to the 4th or 6 or 8. Why am I not saying something like 1 over 1 plus x cubed? What would be wrong if I tried to do 1 over 1 plus x cubed? Why not? Why not? Yeah, it's odd. So where's the dangerous point? For 1 over 1 plus x cubed, what value of x makes you terrified? What number? I'm sorry, -1. In fact, if x is less than -1, you even have a negative number. You can't do 1 over 1 plus x cubed as a probability distribution. You just can only do it on the positives. You can't do it on all of them. Complex analysis allows you to handle that as well. And so I will end with a fun fact. So if we integrate from 0 to 1 of 1 over pi 1 plus x squared dx, this is just arctangent of x at 0 and 1. So does anybody know what angle has a tangent of 1? One of the sine and the cosine the same. What angle? 45 degrees. But we never say 45 in pure math. What do we say? Pi over 4. So you just get pi over 4. No, sorry. There's no pi when I'm doing it like this. It's just pi over 4. And then what angle has a tangent of 0? 0. So it's just pi over 4. So now I'm going to do something a little bit illegal. Does anybody recognize 1 over 1 plus x squared? Does that look like anything we've seen before? What if I write it like this? 1 minus negative x squared. What does that look like? Geometric. So this looks like a geometric with I equals negative x squared. So again, not worrying about whether or not this is legal, it's 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus dot dot dot. We're going to continue and not worry about anything. All right, 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot dot dot. And we'll just say that we'll just do it term by term. 1 dx minus the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x to the 4th dx. Yes, minus the integral from 0 to 1 x to the 6th dx plus dot dot dot. What's the integral of 1 from 0 to 1? 1. What's the integral of x squared? That's going to be x cubed over 3. So that's going to give us a minus a third. What's the integral of x to the 4th? X to the 5th over 5. Plus 1/5. Minus 1/7 plus 1/9 minus 1/11. And that's just, oops, I don't need to have 2 equal signs. So this is the Gregory-Leibnitz formula. It's a slow formula to find pi, but it is a formula to find pi. You can justify this. If you want, don't integrate up to 1, integrate up to 1 minus epsilon, and then everything can be fine. One of the reasons why I wanted to do this in a probability class is if I stop at minus 1/3, the next term, 1/5 beats 1/7, 1/9 beats 1/11. If I stop at 1/3, I underestimate. So here, we underestimate, if we stop at the next term, what do? We overestimate. Does this remind you of anything we've seen? We've seen something like this in probability. Where is this? In calculating these probabilities, we have this kind of alternation that gives us over and under estimates depending on where you stop. What's this process called? Inclusion exclusion. So this is very similar to an inclusion exclusion. And what's nice about this is if you want pi to a certain level of precision, we can do it like this. All right, so this is a great place to stop. So we will stop here. And then